Log on, tune in, find out. Another good idea from Cambridge.
Pleasure to welcome Andrew Mathas, also from the University of Sydney, who will tell us about Carter-Payne homomorphisms for Hecke algebras.
Steve, could you raise the slide, please? I want it later on. Thanks. Okay. Okay, so thank you for inviting me to speak. I want to talk about generalizations of a fairly famous and well-known theorem of Carter-Payne from about 1980. It's been well-known for symmetric groups and for general linear groups for a long, long time, but the Q analog of this result is still not really understood. And I want to tell you of at least one fairly special case of this. So the theorem says something like this. Let's suppose I've got a positive integer gamma and partitions lambda and mu such that we can write mu in terms of lambda. Sorry. So we get mu from lambda just by adding or subtracting gamma to 2 parts a and b. And I want to make one technical assumption. So lambda a minus lambda b plus b minus a plus gamma should be congruent to 0 mod p. I haven't actually said I'm working over field of characteristic p, but I am. And in fact, not just mod p, modulo a big power of p. And then in this case, there's a non-trivial homomorphism between these two spectrum modules. Okay, so I guess the way that I've stated the theorem somewhat prematurely, I haven't said at all what I'm speaking about, so maybe I should go back and do that. So throughout, F is going to be a field of characteristic P, which has characteristic 0 or some positive prime. And I want to define L of gamma to be the minimum positive integer g such that P to g is bigger than gamma. And I guess I really ought to go back a little bit more. So this Sn should be the symmetric group at degree n. And up above S lambda and S mu are spec modules for Sn. Okay, so greater than. Okay, so in characteristic 0, of course, the spec module is irreducible. So in this case, the theorem says nothing because we can't have this condition being satisfied. And in general, what we're doing is we have, let me do it over here. If we draw our partition lambda, it's going to look something like this. Then we have some rows A and B, and in mu, for mu, I want to add gamma nodes here, and I'm going to take them from, let's make that row from here. So to get lambda, I simply take this block of gamma nodes and I move them up from row B to row A. So it's quite an amazing result, I think. Let me sketch the proof. And the proof is really quite miraculous. And it extends a very famous paper of Carter and Lustig from '74. And essentially what this paper does is it defines these weird and quite wonderful determinants and then does a lot of manipulations with them. But these determinants come from nowhere. And I think even today they're not really well understood. But using these determinants, which give you elements at the center of not the symmetric group at all, but of the enveloping algebra of the special linear group, they are able to produce maps between bimodules. And it's a fairly well-known and standard fact these days, but Carter and Lustig also established this at the time. If I want to know homomorphisms between spec modules, this is the same as knowing homomorphisms between bimodules. Well, at least if P is not 2. So this proof really takes place inside the linear group, or the special linear group, the enveloping algebra of it, and it's very tricky to try and see what happens inside the symmetric group. Quite a lot of people have tried to prove this entirely within inside the symmetric group to try and understand what's going on. There is a paper of Stuart Martin and Matthew Fayers that does give a proof. The proof is complicated, and the original version of the paper was almost twice as long, and then they took out details so that they could get it published. And the missing details are not always easy to fill in, but there is in some sense to prove this around. What I want to talk about, though, is an extension of this to the Hecke algebras of the symmetric group, and then go a bit further at the very, very end. So, before I start talking about Hecke algebras, let me naively talk about how one might try and prove this. So the first approach that people use to try and understand Carter-Payne maps was the following. They'd find a permutation module. So you just take the induced trivial representation of a parabolic subgroup of the symmetric group. And these days it's well known and easy to see that if you're looking at homs between two of these induced modules, then this hom space has a natural basis indexed by pairs of standard tableau. Or actually semi-standard tableau. So once you understand this, the spec modules sit at the top of these modules, or the bottom of these modules, depending on whether you like spec modules or pure spec modules. So it's not so hard to see from here that you can get, which way around do I want to go? I guess I want to go here. You can essentially restrict, well, the spec module is a quotient of this in my work. Well, so my spec module is really what most people call a dual spec module. So it's a quotient of this. So any map in here, I can just restrict essentially to give a map in here, and you get a natural basis here indexed by a single semi-standard tableau. And so you could just simply ask, well, when does a map in here give me a map on the spec modules? And it just simply has to be 0 on the quotient when I map from here onto the spec module, and that will give me a non-zero map here. So any map inside here, I should be able to write some sum over t running over some standard tableaus, some coefficients, some theta t's, and there are restrictions on what these coefficients can be in order for it to be an honest map on the spec modules, and one simply has to work out what they are. And there are things you can do which let you determine what sort of coefficients you can get, and so you can really start playing with it and do this. So the real problem here is you've got to work out what these coefficients are, but once you do it, it's clear you have a non-zero map. There's a slightly better, or at least philosophically a slightly better approach to this, which Ehlers and Murray came up with some time ago. So using the approach I've got on the board, which I have sketched only in very, very broad terms, Faes and Martin did actually work out what these maps would be, but it's a highly non-trivial exercise and you've got to work very, very hard. So let me show you another way of doing it, which also has problems. So if we look at this picture, the way I drew it, I said let's take two partitions of n and let's just move these boxes around. That's fine. But we can, instead of thinking about this as a partition of n, we could think about it as a partition of n plus gamma. So now this is a big spec module. And we think about the spec module which has all the boxes everywhere. If we restrict this to an to module for the symmetric group Sn, then it has a spec filtration. And the two spec modules we care about actually appear inside the spec filtration. So we should probably be thinking about this as being an Sn plus gamma module, and then try and think of getting these maps by restriction. So let's just formalize this a little bit. So let's let M be an Sn plus gamma module. Then any element, so let me write F1 to the n gamma. So I just want the submodule of the full group algebra of S n plus gamma spanned by essentially the permutations just where I move n plus 1, n plus 2 up to n plus gamma. So if I take any element, say x, there, this will actually induce an Sn homomorphism of this module. So we can just define rho x to the map which sends m to m times x. And since Sn commutes with x, this is clearly going to give me a map. So if we take nu to be the big partition here, then we can try and use this observation. So it's a completely trivial observation to try and construct homomorphisms. So let's nu be the big partition here. So in terms of parts, it's going to be lambda I plus gamma if I is equal to A, and it's going to be lambda I otherwise. So S nu is going to have a filtration. such that, well, each bit here is a spec module, but let's just say SL modulo SL plus 1 is isomorphic to S lambda, and SM modulo SM plus 1 is isomorphic to S mu as modulus for Sn. So to construct this Carter-Payne map, all we have to do is find some element x in the big algebra that kills off this bit, so I have a well-defined map from here, and has this image, this bit over here. So the kernel of this map, rho x, should contain this SL plus 1, and the image of it should be contained inside Sm. And then this will induce certainly homomorphism from S lambda to S mu as Sn modules. The big problem, of course, is even if you can find such an x here, chances are this map will be 0. So it's very easy to produce such x's. You can just pick anything you like, and it will give you an honest, well, there are definitely some constraints here, but it's not so hard to find such an x. The hard part is checking that the induced map is non-zero. So the problem here, rho x may be 0. But nonetheless, this gives a much nicer philosophical reason for why these maps exist in some sense. They really just come from restricting from a much bigger symmetric group. And as I show you, there's also a very natural choice for these x's. So what I want to do is show you how to do this for the Hecke algebra of the symmetric group. And then, if I don't run out of time, I'll talk about how to do this in a slightly more general context. And I guess before I forget, I should say that everything that I'm talking about here is joint work with Sinead-Lyle. Okay, so let's let H be the Hecke algebra of the symmetric group. I think probably given the audience, I don't need to find it. So just as with the symmetric group, we have spec modules and so each partition lambda then there's a spec module. In the 7 simple cases, give all the irreducibles, and in general, the irreducibles arise as equations of these modules. And so the question is, can we construct maps from S lambda to S mu? So the natural analog of Carter-Payne in this case should be the following. So we take lambda, mu, and gamma as above, so as in my picture on the right-hand side. And we should require that lambda A minus lambda B plus B minus A plus gamma is equal to 0. But modulo what? Well, it's where this E is minimal such that 1 plus q up to k minus 1 is 0. And then in this case, we should be able to find such a homomorphism. So I'm being slightly dishonest here. If p is 0, then I should just ignore this term. So I'm taking the convention that if 0 to the power 0 is 1. Okay. If you allow me to do that, then that's the correct statement, correct conjecture. So 2 cases of these are known. So if gamma is 1, it's the theorem of Lisle. And this was proved using approach 1, and it's a long and dirty calculation. Using Eller's approach, or the Murray approach, it falls out very quickly. You can give a very short, nice proof of this. I'd like to say that I can prove this conjecture in full generality. I can't. And I'd also like to say I can give a nice proof, and I can't do that either. And there's still some awful calculations, what I will give you in the end. Secondly, if this B equals A plus 1, it's the theorem of Edmund and Cox. Well, they prove the analogous statement for the bar modules rather than for the special modules. So these are the 2 simplest special cases of this result, and in that case it's been done. What I want to tell you about is another case where this conjecture is now a theorem. So how does this go? I want to tell you that first. Right. Okay, so first there's a reduction theorem, which, well, I'd like to say technically it's not necessary, but it certainly makes things much easier, and it's possible we can get away without this, but it does make life much easier. So this is an analog of the James row removal theorem for decomposition numbers. If I have 2 partitions such that the sum of the first k parts are equal, then their Hom spaces are easily computed by induction. So this was M. So in this case, I can split up the Hom spaces into an mth part and the rest. So this is really just a truncation functor in disguise. And Donkin has given the right proof of this. He does it using a truncation functor. His result doesn't quite work when q is -1, which is, whereas we have a proof which works in all cases. So the effect of this on this theorem is that we can take this blackboard and we can just get our duster, and we can just knock off the top part of the partition and take A to be 1 and B to be the length of this partition. So it reduces us to this case. So that makes life a little bit easier. Okay, so next, I've said that I want to try and find some nice cunning element sitting inside essentially the Hecke range commutes n plus 1, n plus 2 up to n plus gamma. And I've also claimed there's a natural choice for this. But to make you believe me, I think I maybe have to go back a little bit and say a few other things. So this algebra H is a cellular algebra. I guess this was first proved by Murphy, proved in a different way. Oh no, no, it was first, well, depends how you say first. Murphy proved this was cellular before cellular algebras existed. So this is just a nice way of saying it has a nice basis. Where these S and T are standard lambda tableau for lambda a partition of n. It's not really so important what this basis is for this talk. If you've seen it, then you know it already, and if you haven't seen it, probably I wouldn't give you any more information. So let me just say that it's such a nice basis. This basis actually gives you the spec modules. If you fix the S and let T vary, that's basically a spec module modulo higher terms. So the spec modules are encapsulated in this basis, which is the reason why it's so nice. Now let me define a UC Murphy element to be this following sum of basis elements for the algebra. So these are very, very nice elements which control the structure of the algebra very strongly. We take all of them. It's a large commutative subalgebra. Of H. And these are the elements I actually want to use to construct this map. And this is actually what's nice. The key fact that I need, which really goes back to Dip and James, is that when one of these elements, these UC elements, acts upon this basis, what we get is just a scalar multiple of MST. I'll say what the scalar is in a second. And then we get plus bigger terms. So it doesn't, again, really matter exactly what these things are. What really matters is that these L's, they act in a triangular fashion on this basis. So there are bigger terms in some partial order, which is good. Okay. So I actually need to know what these strange constants at the front are, so let me tell you. So here, Ct of k is just C minus R if k is in row R and column C of t. And if I take bracket of any integer, I just want the corresponding quantum integer, but there are many versions of quantum integers around, so let me just say it this way. Of course, if q is minus 1, you have to be a bit careful, but let me just say this. Okay. All right. And I guess the other fact that I need, and this is very easy to check, it's sort of clear, well, it's not quite clear from definition, but if I take ln plus 1, ln plus 2, to ln plus gamma, all these elements with they commute with everything inside the Hecke algebra on n things, which I consider as a subalgebra of those things inside n plus gamma. So I'm going to construct these maps as products of these UCF elements, which is really quite pretty. If Q is not a root of unity, then the whole algebra is semi-simple. So in that case, nothing's interesting. So the only interesting cases are the root of unity cases. Concomitant of what? Right. Yes. I guess so. And this LK, and it should be the case that this thing commutes, but certainly it does commute with the algebra, say, Kn minus K. And this I think must be the full commutant. And I guess I've never really thought about this, but it must be short of the full commutant. I'd be surprised in some sense if it wasn't. Okay. So I just realized I started not 3 o'clock, but a little bit later. Okay. All right. So let me define essentially the row that I want to do my work for me. So I've got these two partitions, lambda and mu, and I want to use this to construct an element, and it's going to be R. Just a product of elements like this. And so what are these C's? Well, if I look in my diagram, let me draw it up again. So what I'm really doing is because I've reduced the case of everything in the first row, I've got my gamma nodes sitting up here. And I want to move them to, give myself quite enough space. Yeah, so I want to move them down to the bottom node here. That's really what I'm trying to do at the end of the day. So this is my big partition mu, and lambda is the one that I have by forgetting where those are, and mu is the one that I have by forgetting where those are. Okay. So what are these CS's? Well, I have all these removable nodes sitting in the diagram here. And when I act by one of these L's, what I do is I get things which are more dominant, and more dominant really means that I get things where the big numbers are further down the diagram. So what I want to do is push things further down somehow. And so let me label the removable nodes here, C1, C2, C3, so on, all the way up to CR, and then CR plus 1. So the C's that I have in this product, they're going over the removable nodes in the diagram, so those nodes I can pull off so that I leave a partition still. And I take all of these removable nodes except for the one at the very, very bottom. And those are the things that I just buy. And if we think about what this is doing, let me take my favorite example. So I'm taking my lambda to be 442, and my nu to be 6, 4. And so this nu is the the union of both these things, if you like, so it's 642. And then, in this case, my lambda mu, I want to move the big numbers down, so I've got an L11 minus something, and there's going to be two places where it is, so I'm going to have two of those, and then I'm going to have the L12s minus something. And so now I just have to work out what these numbers are. Well, as I read along, this is 0, 1, 2, 3, 4, 5, so this one's a 5, so I'm going to put a 5 in the two cases. And this one is 0, 1, 2, so I get a 2 in the other two places. And the reason why this works is because when I act, well, what does this L12 do to this diagram here? The L12 is going to give me this diagram times this 5 plus higher terms, so that the 5 here is actually going to kill off this diagram and give me strictly bigger terms. But where could this 12 go? Well, the 12 could go here. And so the next factor, the L12 minus 2, will actually kill off the 12 that lives here. If it goes all the way to the bottom, well, it's already dead. In some sense, it's where I want it to be. Okay? But this is guaranteed to do the right thing. The presence of these two factors means that I can't have the 12 either in this position or this position. And in general, I've got my n plus gamma starting off here. Well, it could be there, for example. And when I hit it with all the factors in this product, well, I'm going to force it to go down. It could end up in any one of these spots, but then later up on, I follow it with an Ln plus gamma minus a C2, minus a C3, and so on. So it's always got to be pushed down. So at the very end, it's got to be down here. It could be 0 entirely, but it's the worst it could possibly be when I apply all these things is I get the n plus 1, n plus 2, n plus gamma sitting in the bottom row. Of course, I might start with a diagram where I have the n plus gamma over here rather than being up here, but in that case, it's going to die even earlier because they never go up. They always go down. So this is great. It's clear this map does all the right things. Well, I haven't checked all the right things. But let me, I'll convince you of this in a little while. The big problem is that maybe it does too much damage, in that it's not at all clear this map is non-zero. And that is the really hard thing to check in this case. And yeah, the proof is lovely except for the calculation this map is non-zero. And in fact, in general, this map is 0, or can be 0. Sometimes, just as in the Carter-Lustig world, you have to divide by some horrible things. And to keep track of when you can divide by things, you need to have a lot of control over what this does to not just the nice tableaus in some sense, but all tableaus. So the really tricky part in some sense is making this work in positive characteristic as well as characteristic 0. Because in positive characteristic, you definitely do get denominators that you want to throw away at the end of the day. And if you don't throw those away, this map is 0. So yeah, that's the really hard point. So it's non-zero or divide by something. And so finding the right x is a bit tricky as well, but sometimes we do definitely need to divide by things to get a non-zero map here. Okay. Okay. So what do I want to convince you of? So I can't really go through the argument to show that this map is non-zero because it's quite complicated. But let me at least convince you that this thing has a chance of working. So from what I've said so far, so from simply the action of the L1 to Lk, you can see that the image of, let me just abuse notation somewhat and write L lambda mu for both the map and this element. This is going to be contained inside the spec module. Because really the spec module, when I think about it by restriction, if I move both of these big numbers down to the bottom and then restrict to S10, that basically means I ignore the 11 and the 12. So ignore 11 and 12 here gives me the lambda. If they're down the bottom and I ignore them, I get the mu. Okay? So once the numbers are down here, I am going to be inside S mu, and so the image does live in the right place. What about the kernel? We also need to contain, well, for want of a better notation, let me say the bits which are not inside the S lambda. So these are all the things so I've got my t nu sitting on front, whatever that means, and then I've got some other t, and for these t's, I don't want n plus 1, n plus 2 up to n plus gamma all in the first row. So if I take the span of all those things, these things have to all die. And the crucial observation is that because at least one of these things is not in the first row, I've got an n plus j sitting here, say. So when I hit this with the corresponding c, so n plus j minus c, whatever it is, let's say cs, I'm going to start pushing it down. And, oh, no, it's not this one I want, it's actually C1. When I hit this with this, I'm going to end up with a CS minus a C1 as a coefficient of everything. And because of the condition that I've got on gamma, the condition on gamma basically says that this distance here, that is lambda A minus lambda B plus B minus A plus gamma, that's this distance, that's going to divide this. And so this is going to be 0, since this is equal to 0. So that's where this condition comes in. These differences must be 0, and so that shows that the right things are in the kernel, and so I get an induced map. I guess H. So in this way, we do get definitely a map inside there, and now all we have to check is that we get a non-zero map, and that's tricky. Let me show you what it looks like. Could you lower the slide, please, Steve? And I'll give you some examples to show you the sort of things which go on. So this example on the blackboard here is really the first non-trivial example of things start to happen. And that's the first slide that I've got up here, except it seems to not be up on the screen. It's slowly coming up. So if we take those two partitions, in order to show that we get a non-zero map, we have to basically take the generator of the spec module S lambda, and by restriction, well, so it turns out naturally that the combinatorics here is labeled not by tableau, but by semi-standard tableau. So I've just drawn the semi-standard tableaus. So this is the one which generates a copy of S lambda inside this big spec module. So we need to know what happens to this. And so we have to move the x's down to the bottom. And when you work it out, you get this big linear combination of terms. And that's just what you can compute. So if you work over Laurent polyrings in Q, if we look at the difference of lambda A minus lambda B plus B minus A plus gamma, we get it 7. And so in this case, this map will kill off all the things it needs to, and I get an induced map inside, induced map between the spec modules. So this is going to work for arbitrary p, because if we don't actually use the characteristic anywhere, all we need is that e equals 7 to get the things to work. Okay, so that's good. But the coefficients, as you see, get to be reasonably nasty. Let's take a slightly different example. Let's take lambda to be 4, 3, 3, and mu to be 7, 3. So my big partition is going to be 7, 3, 3. So in this case, I've only got one removable node. That's this one here. So the content of this one is 6. So I've got to look at L10 minus 6, L9 minus 6, L8 minus 6. And when I hit this first tableau with this product, I get this linear combination of modules, or of tableau. If we look at this little numerical thing that we need to work, we get that lambda A minus lambda B plus B minus A plus gamma is now 6. So E equals 2 or E equals 3 will be good, because that would kill off the 6. But if I look at my coefficients, nasty things are happening here. In that I've got all these, well, so they're all going down to the right places. But this leading term here could well be 0. So in order to get a non-zero map, I need one of these coefficients to survive. So these two, all these 2's in front disappear, and so what I get is 0. But of course I can just divide out by the 2, and then this first term will survive, and so I get a map. Okay? So in this case, I need to divide by this 1 plus q in order to get a homomorphism. The other interesting thing about this example is that we can take E to be 3 and P to be anything we like, and we'll get a non-zero map, but this is not a Carter-Payne map. So we're getting maps in this way which are not Carter-Payne maps. So there's something slightly more general, maybe because we're close to a wall that things are special here, but it's working better than it ought to because we're producing maps which we didn't know were there before. Okay, thanks, Steve. That's the end of my little example. Could you raise the slide for me, please? Okay. So I guess I haven't actually stated the theorem I can prove, so maybe I should do that before I leave symmetric groups. So what we can actually prove is not the full Carter-Payne conjecture, if you like, but we can prove the following. So let's suppose that lambda mu are Carter-Payne partitions for gamma. And what's the assumption I need? I need that the gaps between the partitions are big. They have to be at least gamma for all I. And of course, we also need that the distance from the first node to the last node is nice. So then we get a non-zero map from S lambda to S mu. So in positive characteristic, this L lambda mu I wrote down just gives you a homomorphism. Sorry, in characteristic 0 gives you a homomorphism, and in positive characteristic you have to divide by something to get it to work. So that's the result. So it's probably natural to ask or to wonder why we need to assume this quite strong condition. If we allowed gamma to be 1, well, that's still a condition there, but in fact, when gamma is 1, you can prove this directly without any problem. And also when the rows are consecutive, so when b is a plus 1, again, you can give a fairly straightforward proof using these techniques. The problem that arises, and the reason why we need this, is that if you're outside of the region where the gaps are not big, or if you're moving more than one node, or if the rows are not consecutive, you have to worry about Garnier relations. So that there's some sort of straightening that goes on with the tableau, and that makes life much more horrendous. And it also changes the coefficients of things. So in all the cases where the result is known, there are no Garnier relations, and you can prove the result. In the case where it's not known, the Garnier relations play havoc, and I don't know how to deal with them. Okay, so but it's really a bit of a mystery, because if you look at the coefficients that come up, there are these really nice products of binomial coefficients and Gaussian integers that arise as coefficients on these maps. And it sort of feels like there should be some nice general algorithm for just producing these things, but we haven't managed to give one. Okay. So let me finish by very, very quickly talking about what happens in the greater case. So what is the greater case? So I want to change the algebra to start with. So let's let H, and maybe I should label it something like this. Let it be a degenerate or non-degenerate cyclotomic Hecke algebra of type G, L, 1n. So this just means that it's a Hecke algebra attached to the Reith product of a symmetric group and just the cyclic group of order L. So it's some sort of deformation of this algebra, either the degenerate version or the non-degenerate version. And there have been some very spectacular advances in the representation theory of these algebras recently, and namely, Brundtland and Teshchev have shown these algebras are actually naturally Z-graded. And so I'm not going to say very much about this, I think, because there's not so much time. So this is, well, I guess in mathematics we use the word naturally quite often, and often when we shouldn't. Natural here is maybe a slight overstatement. Yes, maybe I shouldn't say naturally. And that what happens is there's this Kovner-Lauder algebra, or this is a cyclotomic equation of it, which has a Z grading, but this algebra is Z graded because it has a presentation, which is quite awful, but each of the relations in this presentation are homogeneous. So we have a nice naturally graded algebra in terms of its presentation, and then there's an isomorphism which is not entirely natural between these two things. So more than this, so this was Brundtland and Teshchev. Brundtland, Teshchev, and Wang then showed that the spec modules for these algebras are also graded. So if we think about this group, we would expect the representations to be indexed not by partitions, but by L tuples of partitions. The same is true for this algebra. So for each L tuple of partitions, we get a spec module, and this spec module has a graded lift. Okay, so once you have these graded spec modules, or in fact even before you have them, you could ask, can we lift the Carter-Payne homomorphisms to these algebras? And the answer is, at least some of the time, you can. So yeah, this theorem is not going to mean very much because I'm not going to give you enough of the details. But the theorem goes something like this. Suppose that lambda is a nice multi-partition. And I want gamma to be less than E. So E is defined exactly the same way as before. Well, it's really built into this Kovner-Lauder setup. So morally, it's the characteristic, or the quantum characteristic. Then is a homogeneous map between these graded spec modules. So since I'm not telling you what nice means, this is not a particularly useful statement in some sense, but I guess all I'm really trying to say is there is a way of lifting this to the greater setting, but there's quite a lot of restrictions in what's going on. So this nice in particular lets you always move nodes, just one node, down partitions in ways that make sense. But it gets more and more restrictive. And basically what nice means is that if you look at the nodes of residue I inside this diagram, they have to be far enough apart in some sense. Okay. Yes. No, the grading is still there in the previous theorem. These theorems are different. So I cannot prove the graded version of the theorem for these partitions. Well, they should be graded, but I can't actually prove it in this case. Yeah, so what I really mean is that if I try to translate this proof into the graded setting, it's not clear to me what to do. And there is a graded map, but well, this map doesn't have to be homogeneous. Yeah? Right, yes. Yeah, but it certainly isn't clear how to relate the two sides. Yep. Yes, yep. No, it has a degree in general. And really, what this definition of nice is doing, again, is avoiding Gardner relations in some sense. Because there are still Gardner relations in the graded setting. They're even worse in the sense that we have no idea what they do, I think. Well, it's not quite true. You know what they do modulo higher terms. With the higher terms, you have no hope of understanding either situation. But the nice means that Gardner relations don't ever enter into the picture. So morally, they're sort of the same setup. And this is defined entirely in terms of the homogeneous generators, but in exactly the same way, in that we have, well, in the non-homogeneous, non-graded setting, we have these LKs. There are analogues of these things in the graded setting, which are YKs, and in fact, they're sort of the same, in that this YK, well, the LK acts by some big matrix where we know what the terms on diagonal are. What this YK is I just rub out the term on the diagonal, leave the stuff up above there, but then also just take certain slices and kill off the rest as well. And then I take a sum of things like this. So there's some sort of idempotency playing around. But morally, the Y's and the L's are sort of the same thing, but these are mangled versions of them. And so you can use these in exactly the same way and just essentially do the same sort of argument. And it turns out for these nice multi-partitions, you can actually cope with what's going on very well. But in general, there's big problems in trying to get this to work in a more general case. The proof of this result is actually almost trivial. It holds for a non-trivial class of partitions, or multi-partitions, but the proof itself is amazingly easy. But to generalize the proof and get it to work in a slightly more general setting is something which we tried quite hard to do and haven't managed to do yet. So it's really quite a funny game. It really is a very, very easy argument in this case, but to try and push the boundaries of what this nice means even a little bit is very difficult. Okay, so I'll stop there.
You know if these sum spaces are one-dimensional?
No, in general.
Have examples of...
No, I've tried to find examples of two-dimensional ones and failed. And I guess in type D there's an example which I essentially got from you by Alison Parker. So they're not in general. Maybe they are in type A, but there's no evidence, I think.
And also, can you sometimes compose your maps and get non-zero compositions?
Yes. I'm morally, if you have your partitions somehow coming from the same big partitions higher up, you just compose these as you go down and it works. So if you can go from here to here by something else, then the composition is the obvious thing.
But is it clear that your maps will multiply
Yes.
and give you a non-zero?
I think it should be. I guess I've never tried to write it out, but I think it ought to work. Because the key point of the proof is you keep track of the sort of leading generator of the spec module, and you always have other terms which are not going to affect things, I think. So you should be able to compose.
Any other questions or comments? So if not, let's